Waves can be very powerful, sometimes destructive. Even the best protection breaks with time and needs to be replaced. So here's an idea. What if the infrastructure that protects us provided power to our homes? Heavy like stone, simple and robust, buildable with local materials, an electric generator, and some welding, with a single moving part. Here's my progress on that idea. In rivers, for centuries, water mills have used a constant flow from one direction. So why aren't there water mills all over the beach? Unfortunately, storms, sand and debris flowing through the water are normal in this environment. Floating things get torn off, rotating things turn, but spin unpredictably. On beaches, water is sloshing back and forth between stones. Water is getting deflected from all directions. Sudden, unexpected splashes are to be expected. The waves get split up, sped up in narrowing channels, or slowly empty into a basin. They can flow over the top of another structure. They can run at any angle to each other. They can come from opposing directions or follow a wall. All this makes their power dissipate during a storm, ultimately protecting the places we live in. Lucky for us, there isn't always a real storm, but we can simulate one in the computer. Even simulate what can't be created in the real world, like this letter S rotating in mid-air. However, it takes a long time just to simulate a few seconds. With a 3D printer, the best candidates can hit real water sloshing back and forth. Alternatively, a very cold winter can be simulated. The rougher the tests during the early stages, the lower the maintenance later on. Ice can move stones and storms can move stones, so one way or another, the devices will definitely change their orientation. That means the protection and electricity generation must continue to work in all those orientations. Although with the small prototypes, whether it works or not is pretty hard to see. Yet with a bigger prototype, trying to read a screen in the sunlight turns out pretty difficult. On the one hand, the prototype gets flooded, gets thrown around and continues to work. On the other hand, I've ruined quite a lot of measurement devices with seawater. That's why the screen stays ideally out of the water and is connected with a cable to the prototype. Still, the screen gets dark when it gets interesting. The other camera gets pushed into all sorts of angles as well. Professional underwater measurement equipment exists, but I need to check really low voltages and I need to monitor the surroundings. Moreover, sensor readings should have synchronized timestamps. These are some of the reasons why I ended up building instead of buying that whole upper part. That camera looks outside, another one looks inside. The power bank has extra protection. Then there's an accelerometer and of course a voltage and current sensor. And as a control screen, a website on a waterproof phone, plus LEDs, just in case. Did we get useful data? Yes, we did. Most importantly, there was no backwards rotation. To be extra sure, a weak generator was used so that the rotator could spin easily. The downside of that is that the readings were also extra low. But that's okay. In many different positions, half or completely underwater, the rotator turns. 30 minutes was the longest test so far, and no stones or sand could stop it from rotating, although I really tried to stop it. That is also something that the patent application process has shown. Other turbines can convert water flow much better to rotation, especially if predicting the direction of the flow is easy. However, stones and sand will easily stop them. The idea in this video might not look so different at first glance. So what makes this idea tolerate sand and stones, slosh and getting topped over? A closer look at the core components reveals the differences. We can see the rotator blade spinning, but if we take the rotator away, the water is still spinning and swashing. Water enters the cylinder through one opening and flows out from another. If we take away all openings but a single one, the water is still spinning. That's because wave peaks enter the cylinder at high speeds and valleys exit at lower speeds. A channel can take a wave head-on or passing by. The shape of those channels funnels and turns the flow into the direction of the spin. The flow gains speed and a jet of water enters the cylinder. In a cylinder without water, the jet will push straight against the first thing it hits. It eventually hits the walls, and soon after there's a rotating pool of water. Any jets entering later add spin to the rotating pool. A spindle without blades will turn with this pool, but won't stop it. More spindle turns come from more pool rotations. Pool rotations come from water jets, and water jets, they come from squeezing water, ideally, smooth and gradually, as sharp turns chop the flow in a funnel channel. The flow can completely stop when there's only a sharp turn, but no channel. So the funnels shape the water and the walls shape the solid part on the other side. That's the heavy part, the part that storms slowly chew on over the years. Erosion will take the device apart, so it can't be too delicate. Parts will break, so each part should have a low environmental impact if it breaks off. In the long run, this device will likely stop generating electricity before it stops to work in its main function as a wave breaker. In the short run, this device needs to generate enough electricity to justify its installation. That's where the blades come in. They are mounted to the middle of the spindle, which minimizes obstructions. Their tips have a distance to the walls that's larger than the openings. This allows small stones to pass through and doesn't block the rotation. Plus, both wing profiles and cylinders work, because unlike wind turbines or watermills, this device doesn't need winged blades to work. It doesn't try to catch a linear stream passing through it. It tries to catch the stream of the rotating pool by angling the blades against that, like a sandwich of tornadoes. Located at the outer edge of the spindle, the blades can take the impulse energy of the water jets at points of high leverage. If a jet is deflected towards the center, it still flows in the direction of the spin. Sometimes one jet can hit multiple blades like that before it dissipates. All that works both when the device is half in the water and when fully submerged. The rotating pool is then instead a cylinder in which a vortex rotates, and the rotator turns with it, regardless of direction, standing upright or laying on the side. Whether I get a patent or not, I think this is an idea worth trying out on a bigger scale in concrete. I'd be glad to hear your feedback.